Now I want to make sure we have some terminology really polished down for our melting and boiling processes. And these are all things that we've seen in other parts of uh, what we've worked on this semester, but I want to pull them all together and have a little bit more of a tidy package. Now, we've seen these phase changes. We've seen melting, that's when you go from a solid to being a liquid. We've seen vaporization, and that's when you go from being a liquid to a gas. We don't say evaporation when it comes to this specific process because this could be from boiling or it could be from evaporation either way. But either way, it's going to be the energy to get the closely packed, interacting liquid molecules to pop apart, go into the gas phase, and be far enough away for the I can't see you rule to take effect. So, it doesn't matter what we normally call the process, the actual energy is going to be called vaporization. And then we're going to have this third process where you go straight from solid to gas phase. We see that a lot with things like dry ice, where we're just totally dodging the liquid phase. It's not even that it's melting and then that liquid layer is immediately evaporating. That's not really what's happening. It's going straight from solid to gas phase. Now the energies are going to add up to be the same as if it did melt, then immediately evaporate. And we know that's true because of Hess's law. These are all going to be path independent since these are going to be enthalpies. But the physical reality does matter as well as the energetic. And the physical reality is sublimation is a single process, not a two-step process. Okay, well, that's great. We see sublimation, so enthalpy of sublimation. Notice when we have this zero up there, that means the standard enthalpy of sublimation. In other words, for that substance, we can just look it up in a table and we'll know what it is under standard conditions. Same thing here and here. Now, all of these are going to be endothermic processes. Hopefully that makes sense to you because we have to put in energy to melt something and then to get it to vaporize. Now, just as an extra example though, I want you to think about this in case you hadn't noticed it before. Have you ever left an ice tray sitting in the freezer for a long time and you were sure that those ice cubes were full when you made them? But man, those things have whittled down. They're only like half the size that they would normally be by the time you take them out. What actually happened? Well, you had some of the water molecules popping off of the solid surface and ending up in the gas phase. In other words, it was almost like they were melting then boiling all in a single process. Now you might say to yourself, wait a minute, there's no way I had boiling water in a freezer after leaving it there for a couple months. And you're right, you didn't. You had sublimating water. What happened is that occasionally the little bit of bumping that they have at the surface as they're wiggling back and forth, just like in a game of pool, when you go to break the balls, one of the balls in the formation is suddenly going to fly off at a very fast speed, while the others stay pretty slow. And that one that had a lot of kinetic energy happened to have enough to overcome its attraction to its neighbor. So from that alone, you can see that the size of this is probably going to depend on how sticky it was to its neighbor. This process should also depend on stickiness, as should this. Now hopefully you'll also say to yourself, well, path-independent processes like enthalpy, they do the exact same amount of energy in reverse when you go for the reverse process. So if we want to think through the exothermic processes, we can have all of those processes with the same energies just going the opposite direction. Now when we're having gas turn into liquid, we call that condensation, but we still call it the enthalpy of vaporization. When we go from liquid to solid, we call that freezing, but we call it the enthalpy of fusion, just like we did over here. Now, why did we use the word fusion? This is a really archaic thing. What ended up happening is, back in the times where we were really coming up with terminology based on metallurgy, because that's what we cared about at the time, was making better swords and things like that, you had to melt together two metals, and in the process you got them to fuse. So when you melted them and then allowed them to freeze and turn solid again, you had fused the metals. So this is known as the enthalpy of fusion for historic reasons. And then deposition would just be the reverse of your sublimation process. Wait a minute, how does that work? I've never seen that in everyday life. Absolutely you have. When you leave that bag of peas frozen in the freezer for a good long time, because you just didn't get around to eating those frozen peas, and finally you're going to use them or throw them out, and you take the bag out, and you notice there's this frost block inside of there around all of your peas. What happened? Well, the water sublimated out of your frozen peas into the gas phase, stayed in the bag. They found another molecule, gave the heat away, stuck to the other water molecule, and deposited and created frost. That's the process that we're talking about when you see sublimation being reversed and you have deposition elsewhere in your freezer.